more closely, so far we've just given friction like as a force in terms of, we're pulling on this box and it has this much friction. Now we're going to dive into friction a little bit deeper. Today, friction, and then next class, inclines, how objects on an incline are affected by forces. And so that's really kind of putting it all together. But friction is an interesting topic for us to start looking at. There are two categories of friction. The first category of friction is considered kinetic friction. What's that prefix kina mean? Movement or motion, right? So if we're talking about kinetic friction, it's friction that is of an object that's already in motion. So this is the friction. It's often called sliding friction, but it's the friction of an object while it's currently in motion. There's a separate type of friction that basically holds an object in place. That's called static friction. But kinetic friction is a friction of an object that's currently in motion. When we look at friction, the magnitude of our kinetic friction force depends on the two surfaces that are interacting, right? That's literally what friction is. It's dependent upon the two surfaces. What are two surfaces that have really high friction? Yeah, go ahead, shout them out.
Carpet and sandpaper.
Yeah, carpet and sandpaper, right? That's gonna make a lot of friction. What are two surfaces that might have really low amounts of friction?
A bar of soap.
Ice, yep, soap, right? Any sort of detergent, things like that. Those are things that lower or have a lower what's called coefficient of friction, okay? But when we look at friction, we know it's actually proportional to the normal force. So here is our equation for friction. Frictional force is equal to the coefficient of either kinetic or static friction times the normal force. Okay, so this is an equation that should go on your equation sheet. I don't usually even put in the type of coefficient. Okay, this little guy right here is a Greek letter, and it stands for the coefficient of friction. Okay, they are predetermined values. Okay, so these are calculated values of two surfaces interacting. Okay, so carpet on carpet would have a high coefficient of friction, and ice on ice would have a low coefficient of friction. Okay, typically our coefficient of friction is a value between 0 and 1. It would be a red flag for us if our coefficient of friction came out at like 10. Okay, so coefficient of friction is typically a value between 0 and 1. Okay, we need to understand that friction is proportional to the normal force. So I want you to be able to demonstrate this a little bit. I want you to lightly rest your hand on your table, just lightly. Okay, so what's our normal force here? Is it having to work really hard? No. So slide your hand back and forth. Right? Do you feel a little friction there? Mm-hmm. But is it difficult for you to slide it back and forth? No. Now increase the normal force. Now try and slide. Right? A big increase in friction, right? Think about it. You're literally smushing those two surfaces together. So now you're forcing them to interact a lot. So the less the normal force has to do, the less our frictional force has to do. The more our normal force has to do, our frictional force is greater. Okay? So that means objects with a greater weight, therefore typically a greater normal force, has a greater a greater frictional force being applied to it. Okay? So we got to think about increase in normal force would mean increase in friction. Okay, the other category of friction is called static friction. You have to overcome static friction in order to get an object into motion. Right? You have to overcome static friction to get it into motion. It has the same frictional equation as the other one, but it says force of friction maximum. We don't ever really write it out like that, but the maximum amount of static friction you have is when it's at rest. And so it has the coefficient of static friction times the normal forces. My, sorry, I don't need this. My subscripts didn't come in very cleanly when this was imported, so we don't have to worry about that. But I don't usually give a distinction between the difference in equations for static friction versus kinetic friction, right? You need to know which coefficient you're working with, but other than that, you don't have to change it. It's the same equation.
Okay.
Same equation. I wouldn't even worry about that one, okay? Which value should be higher between two objects? The coefficient of static friction or the coefficient of kinetic friction? Which gives me a higher value? Which is a higher coefficient? Static friction or kinetic? Static, right? Because it's harder to put things into motion than to keep them in motion, okay? And so my static friction coefficient will be higher. These page values are from my last textbook, so sorry. So I don't have those in there, sorry. I will look for a table in your textbook. Honestly, I didn't even think to do that ahead of time, so that I apologize. Those pages are from my last textbook, so that won't affect us very much. So typically the coefficient of friction will be given to you in the problem, or it will be a value you calculate. Okay, we won't have to go reference a table very often because there's not the mega database. Well, I'm sure there probably is, but not in our textbook. Usually it gives us a table of 5 or 6, right? But usually that coefficient value will be given to us in the problem, or it will be a value that we calculate. Okay, so let's just go ahead and jump in and try some here. Okay, these problems have a few different ways we've got to work through them. Okay, because it could be a 2D problem, it could be regular, whatever. But let's just work through it. Okay. Says a sled with a mass of 50 kilograms is pulled horizontally along a flat snow-covered surface with a force of 75 newtons. The coefficient of friction is 0.010. And so here for these problems, I kind of walk you through what I think the step-by-step is, but our overall goal is to find the horizontal acceleration. Okay, so I kind of walk you through what I think maybe the process should be, but you can get to your final answer a lot of different ways. But first things first is to draw our diagram. So here's gravity. Here's our normal force. It says it's being pulled here with an applied force of 75 newtons. You could call it tension because we assume it's being pulled with a rope. I don't care what you call it, right? But we're pulling it forward 75. And then we have to assume friction, don't we? Because it gives us a coefficient of friction, so we assume that we have friction present. Okay. So I don't care what order you go in here, but why is it going to be important for me to find the force due to gravity? Why do I need that? Because I have to have the normal force. Because in order to solve for a coefficient of friction and to use my coefficient of friction, I have to have the normal force. So I'm going to go ahead and start with that, okay? Do I know, are my normal force and my gravitational force congruent here? They are, okay? So once I find my gravitational force, I can use that to find my normal force. So gravitational force would be mass times 9.8. And so that gives me 490 newtons, which means my normal force is also 490 newtons. Do we agree? Can we make that jump? If it was a two-dimensional problem, we would have to do some more work to find normal force, but we don't have to here. So I've technically got both of those done. Calculate the force of friction. I'm not gonna do that. I don't need to do that separately. Okay, here's what I want to do. I'm going to go ahead and start examining the x direction. And I'll say F net in the x direction is force applied minus force of friction. Can you guys see that green okay? Yeah. Okay. So now I'm going to set up, my goal is to solve for the acceleration. I'm going to sub in here. What do I sub in for F net? What? No. Because I'm going to have acceleration. What's another way to solve for F net? Mass times acceleration. So MA, because I want to solve for acceleration, equals force applied, which is 75, minus force of friction. And what can I sub in for force of friction? What's my equation for force of friction? Coefficient times the normal force. See how we've got lots of different equations? We're going to sub it into the big one, right? My net force equation gets things subbed in. So now I'm going to go ahead and keep going through that. Looks like I might need to change colors here. Okay, M is 50 times acceleration equals 75 minus 0.01 times my normal force. Okay, do we see where those numbers are coming from? I don't need to solve force of friction separately, then plug in that number. Could I? Absolutely. But I just want to do my work in one spot, right? I don't want a bunch of different things happening. I think we can put it all in one spot. So now we're going to go 75 minus, what is this, 4.9 equals 50A. Did I do that math right? Okay, so 75 minus 4.9 divided by 50 gives me an acceleration equal to 1.402. What's my units for acceleration? Meters per second squared. Very good. Okay. So we're going to check here, right? My my acceleration came out positive, which means I'm moving forward in the positive direction. Would we agree with that? Okay. Okay, good. And my frictional force was less than my applied force, so it allowed me to keep moving forward. This part of my problem, right, knowing that those are congruent, that works as long as there's no other vertical force acting, right? No other vertical force making that normal force change values. Okay, comfortable there? This coefficient of friction times the normal force, that's our new sub. Okay, we're putting that in there for that frictional force. Okay, let's try. Did I skip one or is that one? The next one. Okay. 225 kilogram crate is pulled horizontally with a force of 710 newtons. If the crate moves at a constant velocity, what is the coefficient of friction? So first things first, even though you might not always need it, I do encourage you to put a diagram in. Okay. We're applying our force this direction, and we've got friction happening in the other direction. Right? We know it's being pulled horizontally. It's not being pulled at an angle. Our force here is 710. If it says I'm going to be moving at constant velocity, what's that mean about my frictional force? It's also 710, right? So I don't need to I can skip a little bit of my work there, right? Constant velocity would mean that my net force in the x direction is 0. So I know that those two can be called equal to each other. Do we agree with that? Mm-hmm. Are we okay with speeding that step up? Yes, we could write the equation, but if we don't need to, we don't need to. And then what do I know about my vertical forces here? They're equal as well, but are they equal to my horizontal? No. So I might put two, congruency lines to show that they're equal to each other, but they're not equal to horizontal. And so now I'm going to find FG as 225 times 9.8. Why do I need to bother doing that?
Normal force.
I have to know my normal force. So now if I know my frictional force is 710, I know that's equal to the coefficient times the normal force. And so I'll take 710 divided by 2205, and I get a coefficient of friction equal to 0.322. 0.322. And there's no units for coefficient of friction. Is that what you're going to ask? Good question. Here's why there's no units. This is newtons and this is newtons. So when I take newtons divided by newtons, I'm left with nothing, right? So coefficients of friction don't have a unit. Yeah, Charlie.
So if you were to...
We've got a normal force. We are pulling upward on our box at 100 newtons, 40 degrees. And we've got friction. Okay. I like to remember I called these side F applied X and F applied Y. You could shorten that down however you want. Are we going to need both of those values in this problem? Will we need both the X and the Y?
Yes.
I think we will. We'll need the Y component to help us solve for what? Friction and the normal force. And I'll need the X component to help me solve my net force in the X direction. So I will need both of them. I'm going to go ahead and knock both of them out now and break that vector into its components. So 100 times sine of 40 would be my Y component. 64.3, and my X component would be 100 cosine 40, 76.6. Did those values match what you had for your components? Or am I moving too fast?
No, we got it.
Do I need to know FG?
Yeah. Oh, yes.
Am I going to need eventually to know FG?
You do.
So I'm going to take 30 times 9.8, and I'm going to go ahead and solve that. 294 newtons. Does that automatically mean my normal force is equal to 294 newtons?
No.
Not in this case, right? Because I have another vertical force acting. Okay? So how could I find my normal force here? Can you speed that equation up, or do we need to still see it? Right? F net in the y direction would be normal force plus F applied y minus Fg. And so is my object accelerating vertically at all?
No.
It's not. So this would be 0. I don't know what my normal force is. Applied y is 64.3, and this is 294. Yeah, go ahead, Isaac.
What are we solving for? What's the question asking?
Horizontal acceleration. That very bottom bullet says find the horizontal
Oh.
acceleration. That's my overall goal.
Okay.
Okay? Yeah, sorry, I didn't make that clear.
Very good.
So why am I working to find the normal force if my overall goal is horizontal acceleration? I have to have normal force to move forward with friction. So you're going to have to do it, right? So I just want to get it out of the way first. So once I'm to this point, I'm going to take 64.3 minus 294, and I get normal force minus 229.7 is equal to 0, which means my normal force when I move that over is equal to 229.7. What's a faster way I could have done that? Couldn't I have just taken 294 minus 64.3 right away?
Yeah.
Right, that could speed it up. You will always be able to make it work here. I'm just trying to help you kind of look through what's the basics of the math that we're doing, right? And it's getting us to that spot. But you could always work it out with our equation. That works as well, okay? So I've got my normal force. Let's examine the x direction now. Net force in the x direction is F applied x minus my frictional force. Okay, net is mass times acceleration equals 76.6 minus the coefficient times the normal force. Okay, we feel good about what happened here. This is coefficient times the normal force. I'm subbing that in. So that frictional equation needs to go on your equation sheet if you haven't put that on there already. All right, force of friction equals coefficient times the normal force. Do we feel confident about subbing that in? Yes? Okay. And so now I just do my math. So 0.3 times 229.7, 76 minus that, and divide that by 30. And I got an acceleration equal to about 0.236 meters per second squared. Is that similar to what you had? Okay, so we had to take into account work for both the vertical and the horizontal, and that's really because we determined frictional force is dependent upon that normal force. So we have to use both of those things. Okay, very good. Why don't you try this? Why don't you try the next one on your own? Try the next one here on your own. Okay. Very similar to the one that we just did. Okay, so if you've got questions about order, you could look back through that last one. But try this one on your own. I'll give you a couple minute head start, and then I'll put it up here. It won't move because friction doesn't randomly pull things backwards, right? Friction doesn't put things into motion. It stops or opposes motion. So this is an example of this is a really common thing. If we had worked it all the way through and saw that our acceleration can make negative, and most of you did, you were uncomfortable with that, but you were willing to like, okay, it's fine, it is what it is. But you got to think about this. There's no applied force in the left direction, right? It's friction. And so friction doesn't put things into motion and pull it backwards, right? So our answer here, rather than lay out an acceleration in the negative direction, it's just that it's not going to move, right? I'm not applying enough force, 165.8. My applied force is not greater than my frictional force, so I won't be able to put this thing into motion. Because here's the difference. This is a static situation. Had my object been already in motion and my frictional force is greater, that could be true because it could be slowing down, right? I could be sliding across the floor and I could be slowing down. That would work. But this was a static situation, which means my box was at rest and I was trying to pull it into motion. Do we see the difference in those two scenarios? If it already had been in motion, a negative acceleration would have worked because that could have been, I just like pushed it and now it's starting to slow down due to friction. Right, that would work. But it was a static situation, and so from rest was a big key there. It wouldn't have moved. Right, and I put that in there on purpose. But yeah.
So the problem doesn't give us a way to solve for kinetic friction, but gives us the coefficient for static friction. We just assume it's not moving.
That's right. That's right. Yep. If it's static friction, we assume it's at rest.
So, we would just say it won't move.
That's right.
We don't even have to solve it on it.
No, if I determined that my frictional force was greater than my applied force, then I can't give an acceleration because it won't accelerate, right? It won't move.
But could there be a situation in which it gives you the coefficient for static friction, but you end up with an object that is moving?
Yeah, because I can apply enough force to overcome static friction, and there's my acceleration, right? Had my applied force been 195, I would have gotten an acceleration. It would have been that little push forward right when something gets put into motion. But in this case, my applied force was not greater than my frictional force, so it's not going to move. Tricky.